Okay, so kind of jump around a little bit today, doing some different things. One thing, if you're ever, I just wanted to mention because I noticed it this morning, if you ever watch one of the videos on YouTube, and this is going more towards people probably who are not here in class, but if there's ever any audio issues, let me know. I had one of them, and when I view it kind of as I uploaded it, there's no issue, but when I view it like not through my account, like the last 30 seconds, my voice gets super robotic. So if that ever happens, if you see a video and if you're going back, helping Excel or something, if there's ever any audio issues, let me know and I can try to make sure I get those fixed. So what we're going to start out with today is kind of going back to when we first started talking about hypothesis testing. I want to kind of give a little bit of a reminder of what we're doing kind of with type 1 errors and then talk about type 2 errors. Show you a little example in Excel that kind of makes, this hypothesis testing thing hopefully make a little more sense, and then probably work through a couple problems after that. So if we have this assumed true mean, right? And we could do this for proportions, and the assumed true population proportion as well would still apply. Let's say that in fact that assumed true mean, like after the fact, we're able to verify that it is the true population mean. So somehow what we assumed was exactly the right value, right? If that was the case, like that's kind of what, like we're able to see that after the fact. But let's say before we're able to observe what the population mean is, all we have is our assumption and then whatever sample mean we see. Now we can only see one sample mean, right? If we take one sample, we're only going to get one sample mean from it. So what we're saying is, look, even if what we assume to be true was in fact the true mean, if I see a sample mean anywhere in this range, right? If I'm not able to like verify that this is in fact the true population mean, it's just what I'm assuming it is. Well, if I see anything out here, it would be very, very unlikely that this was the true mean, because the probability of seeing something this far away from the true mean would be a really small probability. In fact, we know that we can set a cutoff such that if we see anything that has a probability less than alpha of us seeing that, if the assumed true mean was in fact the true mean, that we're okay rejecting anything in this range, right? If we set alpha, say, to 0.1, any sample mean we find here, right? Once we look up the p-value, because remember the p-value would just kind of be this, if I see this as my sample mean, my p-value is just that area to the right, right? So if we're thinking about this purple area, it kind of represents my p-value. So the probability I saw something that far away from the mean or anything further, excuse me, is so low that it's likely that this wasn't the true mean. Right? So this is how we were kind of setting alpha in our type 1 errors. All right? So for a second, let's go back and let's just have this kind of desired alpha that we set, right? I just want to move it for a second, okay? If we were able to say, like take a bunch of different sample means, what would end, like let's say we could take, I don't know, 10,000, right? What will end up being true is that 90% of the time, if we set alpha to 0.1, I'll get a sample mean that's somewhere in this range, right? And I'll be failing to reject what I assume to be true. However, 10% of the time, I'll get a sample mean in this range. I would reject this as the true mean, even if after the fact I was able to observe and say, well, actually that was the true mean, right? What I assumed to be true was in fact true. I'll be making errors for every sample mean that I would have found out of those 10,000 that had fallen in that range, right? Because if I take 10,000 samples, I'll see a sample mean here, 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 here. I can almost fill out the distribution. So that was the idea of what we were doing with type 1 errors. So that would have been, we're rejecting this as the assumed we're rejecting this as the true value, even though in fact it ended up being the true value. Okay? Type 2 errors, let's say we have that assumption. Right? We said everything in this range, we would have been failing to reject the null. Right? So everything here we rejected, everything here we failed to reject. If in fact the true mean ends up being somewhere over here, right? So we started out, we assumed that this was the true value, but after the fact, we're able to get our hands on some population data and we find out, no, actually the true population mean was way over here, right? Well, then my type 2 errors would have been here, I was failing to reject, even though I should have, in fact, been rejecting that. So you can kind of think about it as my type 2 error would have been everything that I was failing to reject, even though, in fact, I should have been, right? Because if this was the true mean, right, then I should have been rejecting this value. Okay? So you can kind of see how type 1 and type 2 errors would be related, because as I move my alpha to be smaller, right, my cutoff's going to be over here, and now my type 2 errors is going to grow. Right? So if we're thinking about, we're setting our type 1 errors, we're also essentially setting these type 2 errors. And for a lot of the examples that we're working through, we're more focused on type 1 errors. You can imagine, like in the medical community, you might care a little bit more about type 2 errors. If I fail to reject that someone has, I fail to reject that someone doesn't have a disease, that's a big problem, because if they in fact do have it, right, I failed to reject when I should have been rejecting, then they don't get medication or something to help them, right? So, I would say probably more so if you were in, the pre-med or something like that, and you were taking a stats course over there, they probably would focus a little bit more on type 2 errors. But for usually what we're going to do, we're often going to be concerned more with type 1 errors because we're kind of trying to pinpoint down where this true population mean is. And there's not huge repercussions if we make a type 2 error like in the medical community. So that was kind of something that we had talked about a while ago. So this idea of type 1 errors, I want to kind of get at. So let's go. Have this up on Canvas, but there's a file called HT example tuition. So this is just a hypothesis testing example. And I thought this was a pretty interesting thought experiment and hopefully kind of gives us an idea about what we're doing with this hypothesis testing. Right? So let's say I have this, tuition data for a bunch of different universities. I'm sure Ball State's actually on here. Maybe not. Should be. Did I pass it? Yeah, Ball State University. I've got all these different universities. You can look at what their tuition was. And I forget what year. I think the last reported year they had was, here it is, 2012, when they had every single university's tuition. Right? So I can find the true population mean by simply using that average function in Excel. Right? That's nothing crazy. I can find what my sample size is if I was interested in it. I can find my true population variance. Okay. So when we were working with those examples where all we had was a sample mean, but we knew what the true population variance was. Okay. So let's think about doing that. And here, my first sample is going to be these numbers right here. Right. So these were just some random numbers I generated to make some things work over here. But essentially, this first column right here would be like if I randomly sampled 50 of these universities, right? So I don't have, let's assume now I don't have the population data, but I have one sample and I have 50 of the different universities, okay? And it's random. Well, I could find my sample mean, and let's say someone tells me, you don't have the full population data, but you only have these 50 schools, but I do have the population. I can tell you the true variance is what, 76 million, right? So you go, okay, Well, I can take the sample mean I found, right? If I assumed that the mean was equal to this value, like I just happened to get lucky and guess, right? Just kind of like I said here, we were talking about type 1 errors, and I said, let's assume that I guessed this, and it ends up being true. What sample means are we making kind of type 1 errors for? So I somehow guessed the assumed true mean that I have is exactly equal to the population mean. So I turn my sample mean that I found from these 50 universities into a test statistic. I take my sample mean, I subtract the assumed true mean, which we're using that population mean because this is kind of a non-realistic thing where I like happen to guess the population mean exactly right. I'll then divide by the square root of my population variance, which was given to me. And here I just counted these cells. That was just giving me my sample size, right? So this is just our test statistic equation put into Excel. Once I have that test statistic, right, I can find my p-value. And here I set this up as kind of if we did like a two-tailed test, right? So I had two tails. It didn't matter if I found a sample mean that was less than or greater than that assumed true mean. I would find the area kind of that's more extreme than that test statistic. So if I had a negative test statistic, what I was doing was, if I find a negative test statistic, I'm finding the area to the left. If I had a positive test statistic, I'd find the area to the right. And no matter if I had a positive or negative test statistic, once I find the area, it's a two-tailed test, so I had to multiply it by 2 to get my p-value. Okay? So that's how I kind of set that up in that first column for that first sample, right? And this is kind of a trick, right? When I take the absolute value, then it didn't matter if my test statistic was positive or negative. I was kind of always looking at that right side of the distribution, but it doesn't matter, right? Since it's symmetric, the area to the right of the positive value would be the same as the area to the left of the negative value. So, whoops, where am I at? There I am. I get my p-value. I then set up that if statement to say if my p-value here, it's above, is less than, where's that cell up here? The alpha that I set. So here I set alpha to be 0.1, right? If that's true, put a 1 because I should be rejecting. If it's not true, put a 0. So I'll fail to reject. Okay? I then did this, right? So that was my first sample. I then got another 50 random schools. I then get another 50 random schools, another, so on and so forth. And I did that 1,000 times, right? So I have 1,000 different samples here, all of size 50. Here, let me see, there it is, right? So if we're counting up the number, I have 1,000 samples here, all of size 50. For each one, I found the sample mean, found the p-value, sorry, test statistic, then the p-value, and then I made my rejection decision, okay? Yeah.
And so the more zeros you see, the zeros mean fail to reject,
yeah.
the more you would think that that mean isn't right.
If I'm failing to reject, I'm more likely to think the mean is correct, right? Because I've assumed that that's the true mean. So if I'm failing to reject that assumption, what I'm saying is I can't tell you that that's not the true value. Yep. So every time there's a 1, what that's saying is, well, look, here, let's find a 1. There's not as many of them. Here's one. What this is saying is, look, the sample mean I found here was 15,000, right? Well, that's quite a bit above 13,000. So that was one where once we worked it all out, the probability that I saw 15,000 was low enough where I was okay rejecting this as the true mean. So I then just counted up the number here. So let's make this a little bit wider so you can see this. The number of incorrect rejections, which essentially is just my type 1 error, when I'm rejecting even though I shouldn't have been. So all I did there was I kind of added up that entire row, and that would give me the number of times I rejected. But this is like a weird thought experiment where we're able to then go back and look at the population data and say, well, no, what I assumed to be true was in fact true. So here, every time I rejected, I shouldn't have been, right? So I can kind of play around. It'll randomly generate new numbers every time I click on a cell and hit enter. If I can do this. So notice, this is kind of floating right around 100. Sometimes it's a little bit above, sometimes it's a little bit under, right? Yeah.
So we, like, did we want it as close as like the possible be to 13,000?
To say that we want it to be as close, when we take these sample means, I've got 1,000 of them, right? Because I was cheating and I was assuming it was about what, 13K? I actually just assumed it was equal to what I knew was the true mean. We're more often than not, right, these values right around 13,000 are going to be very likely for us to see as sample means. As I get further and further away from that, those values would be less likely, and those are going to be the ones I say, well, look, it's so unlikely that I would see this as one of my sample means. If in fact this was the true mean, then I'm okay rejecting that as the truth, like that assumption. Now, once I count those up, notice it's about 100 out of 1,000. So I guess I could think about this differently. So divide that by the number of samples that I had. So here now all my number has changed, so it goes a little bit, but 98 out of 1,000 I rejected when in fact I shouldn't have been, because I was using an assumed true value that I knew. I cheated, right? I knew it was the true value. So I'm rejecting when I shouldn't have been about 0.098, right? Or 9.8% of the time, which is exactly right around that alpha that I set. Now let's see what happens if I change alpha to, excuse me, 0.1 instead of 0.1. Now I'm getting something a lot closer to 0.01, right? 0.008, 0.009, 0.014, 0.009. And it's obvious it's never going to be exactly that, because for us to get exactly what alpha is in like a little thought experiment like this, I would need an infinite number of samples. Obviously that's not even I can't get an infinite number of samples in Excel, but 1,000 is quite a few, and it kind of shows us like, yeah, this is like right around. We're always going to be making those type 1 errors of whatever we set alpha to. Okay? So hopefully it's just this discussion just kind of is helping us kind of think about hypothesis testing, what we're doing, kind of, I guess, revisiting some things we've talked about. Any questions on any of that before we keep moving? And no, I'm not going to expect you to do something like this in Excel, but it is kind of neat. Like, I think I did this with the confidence intervals, but you can use this VLOOKUP function, generate some random numbers, and you can kind of generate these random samples for yourself. And these aren't just random numbers that I'm generating, right? These were, but that's only so I can use this VLOOKUP, which essentially randomly selects one of these schools. It like kind of behind the scenes, if you want to think about it this way, it like gives each one of these an ID. And then from these randomly generated numbers, it selects those schools that have that random number as that ID. So it's kind of a useful thing to do in Excel. All right. So I want to go through one here. It's a little bit different. So let's do, no, I want to do one that I have the same value repeated. Oh, I do. I have one right here. Okay. So let's work through this first one, right? Doesn't have a lot of context here, but it's something I want to point out. So let's say we have this null and alternative hypothesis. I don't know what this is. Could be undergraduate enrollment, something where we've got the assumed true mean to be 9,200, right? Or 9,200. Or the alternative hypothesis is that it's not equal to that value. If we want to find a test statistic and a p-value and a rejection decision, when we have a known population standard deviation of 620. Okay? We want to do this at the 10% significance level. My alpha would be what? Just 0.1. Okay? So I'm going to set this up using this first kind of set of numbers here. Right? So we find 9,200 as our assumed true value, 9,290 as our sample mean. So what we've got here, oops, grab some markers. Let's see if this one works. Nope. Our assumed true mean, right, if it in fact was true, is what our sample mean should be centered around. I found a sample mean of 9,290. We had a two-tailed test So I'm going to find the area to the left, sorry, to the right of my sample mean and say, well, look, it was equally as likely for me to see something that was that far away from the assumed true mean, but below it. So whatever area I find in this upper right tail, I have to multiply by 2 to get my total p-value. So how can I do that? Well, here, I need to turn this in to my z statistic or my test statistic, right? And the reason why I know I can use that standard normal distribution is because I was given what the population variance was. So once I turn that into a test statistic, I'm using the standard normal distribution. I look that value up in the table. The table will tell me the area to the left. I wanted the area to the right, so I'll subtract it from 1. But then remember, I've got 2 sides for a two-tailed test, so I then multiply it by 2. So what equation are we going to use for that test statistic? And I'll actually pull up the formula sheet here in a second that you're going to have for the exam. All right? So it had something like that. Well, we've got our sample mean. We've got our population mean. Right? Our population variance was given to us. Well, we were given the population standard deviation. So this is a kind of a unique one. So I have the population standard deviation of 620. So when I'm plugging these values in, right, I've got 9290 minus 9200 divided by the square root of I had, was it 640 was that standard deviation? 620? Thank you. Notice this is the variance. So what do I need to do? Square it, right? All I had was sigma. I only had the standard deviation. I'll then divide it by my sample size, which I think the first example was 105. Right? This should give me my test statistic. Okay? So once I have that test statistic, let me see, I think I might have forgotten my calculator, so we're going to do this on Excel here real quick. So this is where I might even show you what you could do, even if you're working on something like on the exam. It's going to use Excel to do the math for me here. Even if I don't want to worry about kind of all the functions we have. So I'll take what? 9290 minus 9200 divided by the square root of 620 squared divided by 105. Right? So 1.49 if we round to the second decimal. So I then go to my z table, look up 1.49, scrolling, 1.4 all the way over to 1.49. I lost what line I'm on. 0.9319. Okay, so that's the area. So 1.49 was our z statistic, or our test statistic. 0.9, I already forgot what it was. 0.9319 was the area to the left of that. We wanted the area to the right. Right? So this is what? 0.0681. We then have to remember it's a two-tailed test, so I need to multiply that by 2. Which is then what? 0.1362. And check my mental math. If I'm making any errors, let me know. So this is our p-value. So at the 90% level, would we reject or fail to reject? For an alpha of 0.1, we always reject if our p-value, remember here we were calculating our p-value, is less than alpha. So is this less than an alpha of 0.1? No, right? 0.13 is not less than 0.1, so I would fail to reject, right? The sample evidence I found wasn't far enough away from that assumed true value for me to think that this couldn't possibly be the true population mean. Any questions on that? If I'm on your way, let me know.
you fail to reject,
Mhm.
that means that the mean is.
I want to be careful how we're saying this. It doesn't mean that the mean is 9,200. It just means that based off what we saw, we can't say that it's not 9,200, right? Because if the true mean was 9,200, the probability we would see a sample mean of 9,290 is about, what, 0.13, so 13% likely, which is not very unlikely, right? Now, it is getting close to maybe being able to say, like, at 90% confidence, we could reject that as the true mean, but not even at 90%, not quite. But, you know, I can say with 85% confidence, I could reject that as the true mean, right? Because 85% confidence would be an alpha of 0.15. This is less than 0.15, so I could reject it with 85% confidence. But typically, you know, we like to be able to get things up to that 90% kind of threshold.
Yeah, I just have trouble kind of with the English of it, like reject.
Yeah, I am too. I'm really
Okay.
confused on the failure to reject.
So let's write this out and think about why the English might be a little tricky. Okay? So I've got my null here was this. Right? So if let's start with the reject.
Yeah.
Right? I know that's not what we're doing here, but let's start with that. If I'm rejecting the null hypothesis, remember the null hypothesis is what I'm assuming is true. Okay? So if I can reject this, what I'm really saying is, yeah, I'm rejecting that the mean is equal to 92,000. So what I'm saying is that it's not. Based off the sample evidence I found, this can't be the true population mean. Right? I reject that. I reject this assumption. Okay? So that one is a little bit easier to think about the rejection, I think.
Yeah.
Right? But if I'm failing to reject that, right? And this is why, you know, I think even in the slides I put, like, we accept it, we're not really accepting that as the true value. We're saying that based off the evidence that we found, we can't say that it's not this value, right? We can't say that this assumption isn't true. So we're failing to reject this, right? But it still could be that that's not the true population mean. It's just based off the sample evidence we have, we don't have strong enough evidence to be able to say that that isn't the true mean, right? Think about it this way. If we go back to the court case analogy, right? There are people that we know have committed crimes that the jury just didn't have enough evidence to be able to convict them, right? They didn't have enough evidence to reject that they were innocent, right? It's kind of like what we're saying here. We're not saying, like when you go through a court, you're not really saying the person is innocent, right? You're not saying they are. You're saying we don't have enough proof to say that you're not innocent, which sounds like it's just semantics, but it is a little bit different, right? We're not trying to prove you're innocent, right? I'm not trying to prove that the mean is 9,200. All I'm trying to do is say, well, look, can I reject this assumption? Can I reject that someone's innocent? I find them guilty, or kind of reject this as one of the possible values. Or potentially, I don't find strong enough evidence where I can reject this. I'm not saying this is the true value. I'm just saying I can't say that it's not.
So, yeah, the only reason I kind of knew that,
Mm-hmm.
like I knew that explanation, but with the zeros and ones in the Excel,
Yeah,
you were counting the zeros then.
I was counting the ones because I added up that row. So if I summed it up, I was counting the zeros, but when I add up a zero, it doesn't add anything.
Okay.
Does that make sense?
Well, I would think that all the zeros that you have,
Yep.
which were failed to reject,
Yes.
means that, oh, that mean didn't make any sense.
If I'm failing to reject, what I'm saying is based off the sample evidence I found, I actually can't say that this isn't the true value, right? Because, think about it this way. In that Excel example, I cheated, right? Because I wanted to set up this scenario where my assumption was in fact true, which, you know, this is very likely that I get it exactly right, but the idea would be I could test against several different values here. Let's say I have this as 9,200, right? I saw, let's go even closer. Let's say I saw 9,100 here. So I can't, not 9,100, I have to be on the other side of it. 9,250 or something. Well, that's a pretty likely value for me to see if in fact the true mean is 9,200. However, if I tested against another value, which was 9,300, like let's say I change this to 9,300, well, that's not very far away from 9,300. I probably can't reject that value either, right? So there's going to be a lot of different assumed true means that I failed to reject based off the sample evidence I found, right? I'm not saying any one of those is right? I'm just saying that it could be one of, it's almost like, here's a way to think about it. If I wanted to go through the trouble and do a hypothesis test for all these different values, kind of right around my sample mean, I'm going to be failing to reject when I see values that are near the sample mean I found. But once I start to get out here, right, I'm not going to be kind of failing to reject these values. These are the values that I'm assuming the population mean is equal to. I'll start rejecting at some point. So if I wanted to do a bunch of different hypothesis tests, what I essentially could do is I'm building a confidence interval, right? I'm saying, look, these values in this range, I fail to reject that those could be the true population means. Once I start to get to values that are kind of outside that range where I'm rejecting, that's almost like a confidence interval. Now, why do we do hypothesis testing instead of just building that confidence interval? Because we can get things like this p-value that allow us to say, well, look, we can kind of pinpoint down based off of just the one sample we found what the probability of different assumed true means would be, right? Because, yeah, I might be failing to reject everything in that confidence, in that range, but if my sample mean of 9,290, I think it was, right? If I assume that the true mean is 9,300, well, I'm going to be able to fail to reject that with at lower levels of confidence, right? Small levels, as opposed to if I saw 9,350. I might still fail to reject this as the true value, but I can fail, it's going to be even closer to being able to reject it, right? So that's kind of why we're doing hypothesis testing and not just building that confidence interval, because we want to be able to kind of reject certain values at different levels of confidence, right? Kind of went down a rabbit hole there. And that's a lot, but I think just this general discussion is good just about hypothesis testing, what we're doing. And even if it doesn't all completely stick, right? I guess technically, you don't, I mean, if you want to be a slave to the formulas, I guess you almost don't even need to really know what's going on, right? I use things, black box something where you don't know what was going on behind the scenes, but you can still use it. Well, that's not great, right? That's a good place to start. And hopefully, as we're kind of getting this discussion, we start to move towards understanding kind of what's going on in that black box or what's going on behind the scenes. But these are good questions.
Yeah, that makes way more sense.
Okay. Any other questions? I lose yet. Where are we at on time here? I want to go through one other example from this slide, and then I want to do something I think would be kind of interesting. So let's say instead I go with this second example, right? It's the exact same thing. I found the exact same sample mean, but now let's assume I did that with a higher sample size, okay? So what is having a higher sample size going to do? Okay? Well, if we think about this, and it's all the same values, but I think it's 285 now. My sample mean distribution, we centered around that value that we assumed it was, which was 9,200. If I take a higher sample, what happens to this distribution? So one of the things when we were calculating the z-score, right? This denominator represented the standard deviation of our sample means. So remember, this goes back a ways as well. If my sample size goes up, 105 to 285, what's going to happen to the standard deviation of my sample means? If my sample size goes up, the denominator goes down, right? I get a smaller variance, right? right? This denominator represents a standard deviation of my sample means. So if the sample size gets higher, this standard deviation gets smaller. Why is that useful? Well, if we think about before, when we found this sample mean, let's say here was kind of, I don't know, I know it's a two-tailed test, but we're just going to think about kind of the area to the right of it for right now. So I had my kind of p-value there. If I have now a smaller standard deviation or a smaller variance, what happens to this distribution? It becomes more peaked, right? So now, let's think about it like this, right? It becomes more peaked. So when I have that higher sample size, it becomes even more likely that if this was the true mean, it's more likely I'm going to be seeing the values around it as my sample mean. So now notice, if I found that same sample mean, but I did so with a higher sample size, what happens to the probability of seeing that sample mean if this in fact was the true mean? It's much, much smaller, right? This kind of area representing now my p-value from problem 2 there on the slides, or when I had that higher sample size. So taking a higher sample decreases that standard deviation or decreases that variance on my sample mean distribution, which in turn, right, visually we can see it's going to make my p-value smaller. But if this sample size decreases my denominator, if my denominator is getting smaller here, what happens to my test or my z statistic? It's going to get larger, right? Because if my variance is getting smaller, seeing that same value will mean that I'm more standard deviations away from the assumed true value. What's the interpretation of a test or a z statistic? It's the number of standard deviations away from that assumed true value. So when I take a higher sample size, I get a higher test statistic, right? Which, if we think about, if I was to convert this into z-values and plot that test statistic here, right? It's going to just push that test statistic out, right? If the test statistic gets pushed out, then that p-value is going to get smaller, right? You can kind of see visually here if we were to draw out the two different problem 1 and problem 2 and the differences in the distribution of sample means. It's kind of easy to see that that p-value is going to get smaller. But really, one of the other reasons why is because if I think about my test statistics getting larger, I'm just going out to an area that's further into the tail, so that area in the tail is going to get smaller as well. So higher sample sizes means I get higher test statistics. You think about it as lower p-values. If my p-value is getting smaller, am I more or less likely to reject the null? The p-value is getting smaller, and I only reject when the p-value is less than alpha. As alpha gets smaller, I am more likely to reject, right? I can't write, so hopefully you heard me say and you know what that is, right? More likely to reject. So this is why we like big sample sizes. Yeah?
Is that what makes your confidence pool stronger?
The sample,
If the sample size is
similar
higher?
idea. Yeah, no, so similar idea, right? Because if my sample size is getting larger, I was able to narrow down the range. Here I'm more likely to be able to reject certain values, which means I was like chopping off the one, the ends of my confidence interval. Yeah, it's a very similar idea. Yeah. Any other questions on that? Okay. And I didn't work through all the values here. We went through the first one on problem 2. You could work through and find what the exact p-value is and prove all this. I just wanted to use that as an example to kind of show how taking that higher sample size, we can kind of see how that's going to affect this. But you could go ahead, plug the numbers in, right? Plug in your new sample size, figure out what the test statistic is, go to the standard normal table, look up, find that probability, and you can kind of prove to yourself that p-value will be smaller and you're more likely to reject. Okay? All right. What's another thing I wanted to do today? We got 10 minutes. Okay. So I'm sure we'll get to some of these questions next week for some review. I got all the 2 practice exams up on Canvas as well as a formula sheet. So I'll start kind of probably picking problems from there next week a little bit to work on as well. But I really just want to focus on hypothesis testing because I think it's going to be the most useful to kind of review. And like I said, we'll use some of these next week as well. But I thought something that would kind of be cool to do. I looked at this yesterday. We'll see what it is today. And the only reason I'm choosing this one is because I think they did get the last election right. So here they've got Biden at 49%. So that's pretty high. I thought like an interesting thing could be, and if we go down here, I believe they had 1,500 voters. All right, so these are the most recent polls of 1,500 voters. So I was thinking about, I don't really actually know. I think the last election it was like no one got, I don't even know what the last election was that someone got over 50%. But right now they're thinking that if Biden's going to get 49%, right? If we had no third-party candidates, this would be an even more interesting kind of hypothesis. Let's say, can we say that Biden's going to get less than 50% of the votes, right? So, did I say 50%? For some reason, I just thought I said 90. I was like, that makes no sense. Okay, so what we'll assume to be true, and I said mean here, sorry, proportion. We'll assume that the proportion of votes he's going to get is greater than or equal to 0.5. If this is true, what happens? He wins. If you get more than 50% of the vote, there's no way you lose, right? So can we reject that, right? If we can reject that, then we think this might be a more interesting election, right? Now we found a sample evidence, right? A sample proportion, which we'll use that assumed true value of 0.5. We found a sample proportion of 0.49, which doesn't look like it's very far away from 0.5, but I mean, we also had a pretty large sample size, right? 1,500 people is pretty big. So even though we didn't, we're not very far away from 0.5, we could be quite a few standard deviations away. It's hard to know until we actually go through. So what do we want to do? We want to turn this into a test statistic or a z-statistic for a left-tailed test, right? Less than sign of the alternative hypothesis. Left-tailed test, we just look that value up in the table and we get our p-value right away, okay? So the equation that we had when we're dealing with proportions is take my sample proportion minus the assumed true proportion divided by the assumed true proportion times 1 minus the assumed true proportion over my sample size, right? Thinking about this as, remember, this is my standard deviation of my sample proportions. So if I've got a pretty large sample size, this standard deviation could be pretty small, right? It could be like 0.005. And if it's 0.005, I'd be 2 standard deviations away, which are pretty far away. Starts to give us some interesting p-values. So questions on kind of just the general setup here. If I'm sorry, I keep getting in the way. Okay, so, and the reason why we knew we were looking to the left here was because we had a left-tailed test. So let's go. I don't have my calculator with me, so I'm going to use Excel just to do that. So we found a sample proportion of 0.49, subtract that assumed true proportion of 0.5, divided by that assumed true proportion times 1 minus that assumed true proportion, divided by my sample size of 1,500, right? Just using Excel to be my calculator here. Like actually, when I set examples up for this class, I usually don't use a calculator. I usually just have Excel open and kind of use it as a calculator, right? I made a mistake somewhere. What did I forget? Square root. Yep. Why did I know I made a mistake? Negative 60 is a ridiculous test statistic, right? I'm 60 standard deviations away from the assumed true value. I mean, I have to be really off of my assumption. Okay. So negative 0.77, right? Negative 0.77, we go to the table. I mean, already, we probably can already kind of allude. So negative 0.7, I think this is the 7 column. Nope, this was. So negative 0.77, 0.2206, right? So we found this to be negative 0.77, 0.2206 is our p-value, right? So can I reject any of my kind of conventional alphas here? Well, usually we have alphas of what? 0.1, 0.05, and 0.01. Is my p-value less than any of those? It's 0.22. Is it less than any of those? No. So I can't reject my assumption, right? So if I can't reject that the true population proportion is greater than or equal to 0.5, you know, it's likely that it could be, you know, I'm saying that 0.5 or any value higher could be kind of, oops, sorry.
Then your alternate hypothesis is likely.
Well, no, remember I'm failing to reject here. So it's not that this is necessarily likely. I'm just saying that based off the sample evidence I found, I couldn't reject that the true population proportion is in fact higher than 0.5 or 0.5 or higher. Yeah.
So, okay, the p-value being 0.2206, is that when we say like with 98% confidence?
Not 98, but with what, 78% confidence?
Oh,
Yeah, I know what you're getting at though. Yeah, you could say with 78% confidence, I can reject this is true, right? So, I mean.
So we're using the p-value when we're saying what we're
Yeah,
rejecting.
you can think about it that way. Yeah. We're using the p-value to be able to say, can we reject at the 90, 95, or 99? But you're right, if I'm only rejecting when the p-value is less than alpha, I can think about here, well, if my p-value is 0.22, what's the last, or 0.2206, what's the last alpha that I could reject at? Well, I only reject if it's less, so like 0.2207, technically 0.0000, you know, 0.06000001, but this is a good thought experiment. So really it's like, kind of my cutoff here is around 78%, just a little bit below 78% confidence, right? Which isn't, I mean, it's not great, but it's something, right? But we don't really have strong evidence to kind of be able to reject that this is a true possibility. So it could come election day, we could see, you know, the sample proportion be 0.5, maybe 0.51, right? And we could start to play around with this value. I'm sure like if we looked at like 0.54 or something, we could reject that. But getting 50% of the votes here, we couldn't actually reject. Okay. Any questions on that? Okay. And you kind of imagine like if we only did really have two candidates, this would like kind of help us like almost be able to predict kind of the election to a degree. Although those values are pretty close to 0.5. So it's not, polling data doesn't really give us a lot of ability to say much this year. So I think I'll end it there. Hopefully, like I said, just like seeing things from different angles, hearing things just described, and like, I'll be honest, like I appreciate the questions and stuff because you're going to get as much out of this as like you kind of bring into it, I think. Like I can go through things, but when I don't, you know, if you're not kind of letting me know exactly what you're not understanding, and even if you don't, the question you don't think has any relevance, I at least can kind of see like what you're thinking about and try to explain something a different way to kind of connect with that, right? So more feedback is great. If you have any questions, always feel free to email me or set up a Zoom meeting or anything. Other than that, I'll see you guys on Monday and have a good weekend. Also, I'll probably get up an online quiz today as well. It'll be like really easy question just to kind of get on and make sure we're getting
There
kind of.
wasn't one for today.
No, there wasn't one on Wednesday. Yeah, we didn't really go through enough to where I could kind of get something out there.